focus on polynomials and how we can model with them and different aspects that we can grab from information from our polynomials. It's important that our polynomials are written in descending order. We also want to point out that a couple of things happen. We want to make sure that our functions are continuous. Well, what is a continuous function? A continuous function doesn't have any holes or gaps. It's just one nice, smooth running look to it. An example of a not continuous function, notice we have a hole here, we're jumping. We have another hole and now we're jumping, but yet we're continuing on. This is an example of not continuous. Also fun to note that all polynomials their domains are all real numbers. Once our polynomial is written in descending order, the leading term tells us the direction in which our endpoints will happen. Are they both going up? Are they both going down? Is one going up? Is one going down? And how might that look? We need to first write our polynomial in descending order and then take a look at the leading term. Depending upon if our leading term is a positive value or a negative value, will help us determine then if we're going up or down for our ends. And then we also have to look at the exponent. Is the exponent even or is the exponent odd? When I look at my first example here so that we can match them with the graphs, I see that 3x to the fourth minus 2x cubed plus 3 is already written in descending order. So now I can look at my leading term. I see that my exponent is even, so I'm going to look already at this row, and I see that my coefficient is positive. So I know with my positive coefficient and my even exponent that both ends are going to go up. It looks like the only graph that compares with that is letter D. Both ends are going up. Now, the leading coefficient test, the leading term test here, doesn't tell us what happens in between the two end values. It just tells us which way that graphs are going to go as far as the end values are concerned. Part B, we have negative 5x cubed minus x squared plus 4x plus 2. I see it's written in descending order. So I'm going to look at my leading term here. My exponent this time is odd. So now I'm going to look at the bottom row here. And my coefficient is negative. And my coefficient is negative. So the left side is going to go up. But the right side is going down. So part B would be the correct graph. All right, letter C. I have x to the fifth plus 1/4 x plus 1. Written in descending order already, so I'll grab my leading coefficient or my leading term here. My exponent is odd. My exponent is odd, but my coefficient is positive. It's a positive 1. So the left will go down and the right will go up, giving me graph A. And finally, by process of elimination, but we'll go through anyways and look and talk through it, I have negative x to the sixth plus x to the fifth minus 4x cubed. It's written in descending order, so I'll look at my leading term. My exponent is even. However, my coefficient is negative. So in both instances, both end values are going down. So then part C would be our result. Our next examples is to determine whether each of the numbers 2 and -5 is a zero of our polynomial function. Remember that a zero is when we cross the x-axis. So if that's true, let's say we have a polynomial here, and just kind of draw a nice little sketch of what one might look like. Where it's crossing the x-axis at these values here would be a number for our x value, but notice our y value is 0. So if it is a function, when I plug our x value in, we should end up with 0 for our y value. When I plug in x is 2 and x is -5, hopefully our y value is 0. If it is 0, then it is a zero of the function. However, if it's not equal to 0, then it is not a zero of the function. So let's try out 2 into our function here. 2 cubed plus 2 squared minus 17 times 2 plus 15 is 8 plus 4 minus 34 plus 15. Oops, 8 plus 4, excuse me. When I add all those values together, I end up with -7. -7 is not equal to 0, so the point to -7 would be somewhere down here. That's not on the x-axis, so this is not a zero of the function. But let's try -5. -5 cubed plus -5 squared minus 17 times -5 plus 15. When I take the cube, the square, and multiply, then add everything together, I get 0. So since the point -5, 0 would be somewhere on, let's say here, the x-axis, this is a zero of the function. And remember, a zero, x-intercept, and solution all mean the same thing. So 0, x-intercept, and solution all mean the same thing. This can be kind of tedious, just randomly plugging in numbers to see if they are zeros. There is another way with which we can do this. Let's find all of the zeros of this given function. I've got f of x is equal to 5x, or 5 times x minus 2 times x minus 2 times x minus 2 times x plus 1. Whew, that's a lot. That's also the same as, notice that I have 3 x minus 2's being multiplied together. So there are 3 copies of x minus 2. Okay. It's already factored for us, which is really great. So since it's already factored for us, we can set each factored piece equal to 0. Well, notice how if I were to put 5 equal to 0, that doesn't work. So we don't need to include 5. But when I set x minus 2 equal to 0 and x plus 1 equal to 0 and solve, I get the values of 2 and -1. I also see that 2 has a multiplicity of 3. It has a multiplicity of 3 because it's included 3 times. -1 has a multiplicity of 1. It is 1 that it's up there. Even though we can't see it, we know it's there. Let's find the zeros of negative x minus 1, x minus 1, x plus 2, x plus 2. So I'm going to group the similar ones together. Here and here, they both have 2 of them. Again, I have that -1. If I set it equal to 0, it doesn't make any sense. We can ignore it. But when I set x minus 1 equal to 0 and x plus 2 equal to 0, we have the two solutions of 1 and -2. 1 has a multiplicity of 2, and negative 2 has multiplicity of 2 as well, because they both are to the power of 2 here. Our next example, find the zeros of, and I'm sorry it's not showing it for us, of x cubed minus 2x squared, and what I'll do is just rewrite it. There we go. X cubed minus 2x squared minus 9x plus 18. What I need to do is we need to factor this. So notice I have 4 terms, so we're going to factor by grouping. I'm going to group my first 2 terms together and my second 2 terms together. And we're going to factor by grouping. When I look at x cubed minus 2x squared, I see they're both divisible by x squared. When I factor out their greatest common factor of x squared, I'm left with x minus 2. When I look at negative 9x plus 18, their common factor is negative 9. So when I divide by negative 9, I'll end up with x minus 2. Notice now that with our common factoring here, I created a common binomial of x minus 2. So I'm going to factor out the common binomial of x minus 2, and what's left over is x squared minus 9. And I can factor this one more time using the difference of perfect squares. So x minus 2, x plus 3, x minus 3. Once we have it factored, we can solve and set each piece equal to 0, providing us with 0, 2, negative 3, and 3 when I set each piece equal to 0. Our solutions then are 2, negative 3, and 3, all with multiplicity of 1 because they all occur one time. We can also graph using Desmos to verify. So I'm going to pop over to Desmos and plug this equation in just so we can see that it truly does work in that manner. On the left, I'm going to put in x cubed minus 2x squared minus 9x. We see our graph is building here, plus 18. I'm going to move my graph over a little bit, and I can see then that the places with which my graph crosses the x-axis are in fact how I factored and determined them, negative 3, 2, and 3. Find the zeros of x to the 4th plus 4x squared minus 45. Again, we're going to have to factor. It has 3 terms, so when I look at factoring this, I want to find 2 values that multiply to negative 45, but yet add to 4. 2 numbers that work are 9 times negative 5, and 9 plus negative 5 is certainly 4. Notice then that I'm going to use x squared minus 5 and x squared plus 9. If I were to distribute this, I would take x squared times x squared, which would give us our x to the 4th. X squared times 9 is 9x squared, again obtaining that middle term value. Now that we have it factored, we can't factor any further. We're going to use the zero product rule. I'm going to set each piece equal to 0, and then I'm going to solve. So x squared minus 5 is 0, x squared is equal to 5, or x is equal to plus or minus the square root of 5. When I look at 9, x squared plus 9 is 0. X squared is equal to negative 9. Taking the square root of both sides, I'll have plus or minus 3i. Imaginary values. So my 4 solutions are negative 5, negative square root 5, square root 5, negative 3i, and 3i. Notice that I ended up with 4 solutions. That is directly correlated to the highest power which I see. When I look at previous examples, in example 5 here, the highest power we had was x cubed, and we found 3 solutions here. So the highest power we see should be how many solutions we have. They could be imaginary solutions and they could be real solutions, so keep that in mind. Let's approximate the zeros to 3 decimal places. When I look at this function, I have negative 0.1x cubed. So because I have x to the 3rd power, and that's the highest power we see, there will be no more than 3 zeros because the degree of the function itself is 3. So when I graph this using Desmos, I should find hopefully 3. They could be imaginary ones, and we'll talk about what happens if we verify the graph and then there's only some real, but I know that I need more that are non-real. How do I find them? We'll get further into that later. So I have 0.1x cubed, x cubed minus 0.6x squared minus 0.1 x plus 2. Here we have 3 zeros. We have 1, 2, 3 zeros. We should have at most 3 zeros because we have x cubed, and they are at negative 1.68, 2.154, and 5.526. We have the polynomial function 0.5t to the 4th plus 3.45t squared minus 96.65t squared plus 347.7t. And this can be used to estimate the number of milligrams of pain relief med, ibuprofen, in the bloodstream, t amount of hours after 400 milligrams of the med has been taken. Find the number of milligrams in the bloodstream when time is 0, half, 1, 1.5, and so on up to hour 6. Round the function values to the nearest tenth. And we're going to go ahead and use the table feature in Desmos to help us answer these questions. So now that I'm in Desmos, I'm going to put my equation in on the left-hand side. We're going to have 0.5x to the 4th power plus 3.45x to the 3rd power minus 96.65x squared plus 347.7x. And I'm going to use the table feature to help us out. To get to the table feature again, we hit the settings button and then hit the table. So we can then find our values. We need 0. So when 0 time has passed, that would mean that 0 part of the med would be remaining, or excuse me, would be there because it hasn't been taken yet. Therefore, when I have 0.5 after half an hour, we should have 150 and about 0.2 or 0.15 milligrams of the medication left in the bloodstream. As now time is progressing, to 1 hour, we now have 255 milligrams in our bloodstream. At 2 hours, we have 344 milligrams in our bloodstream. 2.5 hours, we're descending. So we've reached our peak then. Between 2 and 2.5 hours, it's reached its peak in our bloodstream, and now we're going to keep falling. After 3 hours, we now have 306 milligrams. At 3.5 hours, we have 255 milligrams. After 4 hours, we're drastically decreasing to 193 and 2/10. 4.5 hours, we now have 126 milligrams. After 5 hours, we have 66. And after 5.5, we're at 20. And when we hit 6 hours, it has now left our bloodstream. And we can see how those pieces come together with our graph here. We can see the very tippy top there at 2.149 hours. The maximum in our bloodstream is 345 milligrams in our bloodstream. And then it falls back down until we reach 6 hours. We should get a little closer here. 6 hours, we will then have 0 milligrams left in our bloodstream. Going back then to our question, you can fill in the table at will here. Find the domain, the relative max and where it occurs, and the range. So we found a few pieces here. We need to think about the application of finding our domain with respect to the problem itself. Our domain for time, again, our domain is time. Our domain is time, and our time was from 0 hours to 6 hours, from the time we took the medication to the time the medication left our bloodstream. We used the maximum feature in Desmos, and we found that the maximum amount that we had in our system was 345.8 milligrams, and it occurred approximately 2.15 hours after we took the medication. We can then say our range was from 0 amount of medication in our bloodstream to 345.8 milligrams, because again, the range represented the milligram of meds in our bloodstream in the context of this particular problem. Army personnel on active duty. U.S. Army personnel on active duty makes up approximately 37% of the total number in the U.S. military. Mid-year numbers in thousands of U.S. Army personnel for selected years are listed in the table. From 2005 to 2014, notice our X values are listed as 0, 2, 3, 5, 7, and 9, which would be the value of the year after 2005. And that the Army is listed in thousands. Let's model the data using a quadratic function, a cubic function, and a quartic function. Let's let the first coordinate of each data point be the number of years after 2005. Then, using our r² value, which is the coefficient of the determination, to decide which function is the best fit. Enter the data in the table feature using Desmos, and we're going to use Desmos to help us model this data. I'm going to clear our data out, and I'm going to add in a table of values. Our X values were 0, 2, 3, 5, 7, and 9. and their respective y values were 492 and 7/10, 522 and 0, 539 and 2/10, 566, 550 and 1/10, and 512 and 1/10. Using the formulas that were given in your notes, we're going to use, just like we did when we were finding the line of best fit with linear functions, I'm going to use y sub 1, and I'm going to say that that's approximately equal to ax sub 1, and then I'm also going to raise that to the squared power plus bx sub 1 plus c. Here our r squared value is 0.9281, and it gives us the coefficients of the quadratic formula or the quadratic form here. I'm going to go back to our parts here. Here our r squared for the quadratic function was 0.9281. Our a value was negative 2.69546. Our b value was 27.481, and our c value was 486.739. So using our a, b, and c then, our quadratic function would be y equals negative 2.69546 x squared plus 27.481 x plus 486.739 when we write it in quadratic form. Let's see what it might look like if we use a cubic function. I'm going to leave those values up there, and we're just going to move to the cubic function. So y sub 1, so I know where my data points are coming from the table, is approximately equal to ax cubed, and I'm going to put my cursor back by the x so that I can put the sub value back to 1, plus bx sub 1, because that needs to tell the graph where our values are coming from, but this x value is also squared, so I'm doing a sub and a square, plus cx sub 1 plus d. Again, grabbing those values and this right from our notes. This time, our r squared value is 0.981. This value is getting closer to 1, so far a cubic function is certainly the better option. And let's look at a quartic function. So I'm going to go down to our last line here. I'm going to say y sub 1 is approximately equal to ax sub 1, except this power is going to be to the 4th power since we're looking at a quartic function, plus bx sub 1, and this x now is going to be cubed, plus cx sub 1 squared plus dx sub 1 plus e. So notice that as I'm adding more and more values here, I'm just adding more and more letters. But notice that I have the fourth power, the third power squared, first power, and then no powers with each one of them. And the sub ones are just telling the data where I need to put my data points. Which values am I pulling from? And I'm pulling them from the first chart that we created. Notice that our R value, it also gives us the, it gives us R squared is equal to negative 66.7. Well, right off the bat, then that one's not going to work. Our closest one to the value of 1 of R squared is the cubic function because 0.981 is closer. A quadratic function is a nice fit, but a cubic function is a nicer fit since it's closer to 1. So we can say that the cubic function is closest to 1, so it is the best fit. Okay, so I'm going to graph using the cubic function, grabbing the values that they give us, and then we're going to determine f of 1, f4, f of 4, f of 8, etc. So I'm going to just delete these two values here. And in here, I'm going to say y is equal to, using our a, b, c, and d values. So I'm just going to say y is equal to negative 282.469 x cubed plus 1.06316 x squared plus 15.4281 x plus 491.727. And if I back my graph up, we'll see that the graph certainly does go through those points pretty close. It's a pretty close fit to those points there. Now I'm going to get rid of this value here so that I've just got my data values and I've got my equation. I can now use the table feature based on this graph. I'm going to get rid of this table, and here I'm going to add my table to the equation with which we have created. So I can find out f of 1, which is given. So we could say it's approximately $507.9 thousand. When I look at f of 4, we have 552.3 thousand. F of 8, based on the years, is 538.5 thousand. And then 15 years is 9.02 or 89,000. So when I'm looking at my values here, the estimates for the year 2006, which is 1 year after 2005, 2009, and 2013 appear to be fairly accurate to the graph, the 500,000 mark. However, 2020, which is f of 15, doesn't seem reasonable to the data. Notice that it dropped drastically in 2020. So this is not a realistic value. So we have to be careful when we're using polynomials and what we're grabbing information from, because in 2020, when we start gathering more data, we may need to alter the type of polynomial that we're working with to fit the data in a better feature. So be careful again with when the data works and when we might need to think about using a different model to model the data with which we have. And this concludes our lesson on polynomials and modeling.